Hello, everyone, and welcome to today's webinar, where we will be myth busting in the H2 fueling economy. My name is John Butler. I'm the Communications Manager for Clean Energy at Swagelok Corporate, and I will be your moderator today. Hydrogen holds a unique distinction of being the world's only viable fuel source that can meet the performance criteria of light and heavy-duty vehicles while having a net zero impact on CO2 emissions. However, the growth of the H2 fueling economy is subject to many misperceptions that may be hindering its global growth. Myths persist around hydrogen's efficiency, safety, cost effectiveness, and environmental impact as a fuel source. Overcoming these myths will be crucial to propelling the industry forward. In today's webinar, Chuck Hayes, the Principal Applications Engineer for Clean Energy at Swagelok, will discuss common myths about the hydrogen fueling economy and take a close look at the role that fluid system design and engineering can play in overcoming persistent and unique challenges that are presented by hydrogen fuel in the mobility sector. First, we will give you a brief introduction to Mr. Hayes. If you go to the next slide, please. Chuck Hayes is a 31-year veteran of the Swagelok Company. He has spent the last 25 years developing a wide range of fluid system products. In the past 20 years, he's been focused exclusively on fitting technology for alternative fuel applications. He currently holds 7 US patents and numerous patents internationally. He's an active member of the CSA on committees for both compressed natural gas and hydrogen, and has recently been the chair of the HGV 4.10 Committee for Fittings. He also sits on the ISO TC97 Technical Committee and participates in international working groups. During his time as Principal Applications Engineer for the clean energy market, Chuck has supported numerous on-vehicle platforms as well as a wide variety of global projects. Today, he concentrates most of his time on the development of hydrogen mobility solutions for both infrastructure and on-vehicle applications. Just some general housekeeping before we get going. Following the presentation, we will have a short question and answer session. So you can just type your questions into the meeting chat box and remember to hit click when you submit. Please have your microphones muted and your cameras off. And with that, I will turn it over to Chuck Hayes. Take it away, Chuck.
Good morning. Well, good morning here in Cleveland, and good afternoon and good evening in other parts of the world. Well, welcome, and today we're going to be talking about some of the myths around hydrogen. So we've tried to collect quite a few of them, and we're going to be talking about them and how these factors persist and misinformation that's going out into the market. So a few of the areas we're going to look at is we're going to look at safety of hydrogen, the viability as a mobility fuel. Cost and both relative and real terms moving into the future, as well as its environmental impact. So today we'll be addressing each of these topics, kind of to set the record straight on some of these different discussions, and why we believe hydrogen is the best path for the global economy moving forward, and as well as a worldwide focus for helping us achieve greener, more sustainable future, meeting the various governmental goals, including the Paris Accord and other requirements that are coming out throughout the world. So just a quick overview of the hydrogen economy and where things are throughout the world. This graph starts a little bit interestingly. It actually starts in the lower. I start in the lower right-hand corner where we talk about creating clean hydrogen production, and we can do that by using a variety of different sources. We can use green energy from clean carbon-free electricity, biomass, or natural gas. That hydrogen goes into end uses where it can then be used in industry, can be used for transportation. It's being used for removing of carbon-based energy sources in a lot of different places. One of the most interesting ones is glass and steel to replace the the carbon-based fuels that are used for dealing with those high heat applications. There's also another piece that comes into this, which is capturing CO2 before it goes up into the atmosphere. And we're looking at different ways to be able to do carbon capture and put those into permanently either geologic structures or other interesting engineering ways to be able to use that carbon in other ways. So there's an entire universe around hydrogen that's more than just the gas or the liquid form of hydrogen. There are industries that can use it in a lot of different ways, and there are a lot of different options as we move forward to help reduce carbon within our global environment. So let's start off with the first myth. So the first myth that we talk about is that hydrogen gas is hazardous, or it's dangerous, and it's dangerous to store, it's dangerous to use, it's dangerous to move around. Well, in all honesty, hydrogen is really no more different or more dangerous than any other flammable fuels that we use, gasoline, propane, and other fuels that are all oil based, as well as things like batteries. So this is kind of a neat picture that shows a hydrogen fire starting in a test off of a vehicle. What you'll notice is there's two different cars and both of them ignite. The hydrogen is actually venting appropriately straight up in the air. And it is got a hydrogen flame that goes out in a very short period of time. The hydrogen's under pressure, it makes a flame, and then it goes out. The car, on the other hand, because of the density of the gasoline or diesel fuel, will actually go leak out under the vehicle and then continue to perpetuate that fire till at 90 seconds. There's not much left of that car. I did not put any pictures in, but there's some really great pictures out there of also what happens with batteries. So battery electric, especially lithium batteries, burn very hot and for a very long time. So any accidents with full battery vehicles can really lead to pretty significant fires. So there are hazards with every fuel, but the way we handle them is important from an engineering standpoint. One of the things about hydrogen that's really important to understand is hydrogen is really the lightest element that we know of. It's 14 times lighter than air, and 57 times lighter than gas vapor. So something different. So let's say you have a hydrogen tank on your vehicle and you were to have a rupture. That hydrogen is going to go up and away and disperse greatly. So it disperses at a 35 times rate into air. So it's not only going to go wide, it's going to go up and it's going to kind of get out of the way. You can't trust on that to give all of your safety. However, it is a very nice feature of hydrogen that it's got such a great buoyancy relative to air. Unlike that, like we just saw in the picture ahead, gasoline or any other liquid fuel will just drip on the ground and cause a fire underneath whatever that vehicle is that you have. So that's one great feature of hydrogen. Another interesting thing about hydrogen is, and people worry about this because most fuels that we use are actually toxic to humans. Gasoline vapors, diesel vapors, so forth are not good for the human body. Unlike those other fuels, hydrogen is non-toxic, and if we have a hydrogen spill or leak, it will not contaminate the environment or threaten the life of humans or wildlife. Unlike other fuels, if you drop gasoline, now you've got a problem with that getting into the water. One drop or 1 teaspoon of gasoline can contaminate thousands of gallons of water. So as we look at other things around hydrogen, it's just its nature. The hydrogen flame is an interesting thing. So if hydrogen does get on fire, first of all, the flame is very, very pale blue, kind of hard to see in bright sunlight, but it is not as hot as like a gasoline flame. So there is the potential that you don't have as high a risk for secondary fires to occur. Um, Also, hydrogen it burns quickly, so the flames will burn out fairly quick. And unlike that vehicle we saw earlier with the fire underneath it for gasoline, there's a secondary fire there, and everything in that car is burning. And hydrogen doesn't really do that. There is designs within hydrogen vehicles to have venting systems that vent up and away. So even if there is ignited flame on one of those vents, it's up and away from people. So the there's always the question, isn't hydrogen explosive? We have the hydrogen bomb. Well, the hydrogen bomb isn't actually made of hydrogen. It's still breaking the atom apart. It's kind of a misnomer in the way it's stated. But hydrogen can be explosive, like many other items, but it takes an oxygen concentration between 18 and 59%. It's actually optimally explosive in the area of about 24 to 26% of oxygen. But in comparison, gasoline is explosive at an oxygen concentration of 1 to 3%. So when we compare different medias and different hazards, hydrogen is actually uh, much less hazardous for that explosion area that we see within those percentages. There's one other piece that people sometimes talk about, and they uh, confound the two different concepts of explosion and BLEVE. So BLEVE would be when you release sudden release of high pressure. That's something a little bit different than explosion. Explosion is actually fireball blowing up versus releasing of pressure. We do have high pressure containers in the systems. Those have a lot of safety mechanisms built into them to avoid overpressurizing and releasing into the environment. So, one thing people say oftentimes is, "Wow, this stuff has got to be hazardous to move around, and we've got pressurized gases." Well, the fact is that we've been moving hydrogen for years now throughout the various industrial uses that hydrogen has been used for. So you'll see a large tanker truck on the upper right. That's a particular truck for a British Oxygen using long cylinders. The other two pictures are showing cylinders that are on tops of buses. So these buses, the red one is actually a single decker version of the famous red buses in London. And there are a numerous set of hydrogen buses now running around, both double deckers and single deckers in London using hydrogen today very, very successfully. So there are tanks that are designed. Those tanks are designed in a few different forms to be extremely safe. There's extensive testing that's done on all the tanks to be able to make sure that they're safe and that we can move the product safely throughout. There's also devices on each one of these tanks, on the ends of the tanks, they've got thermal pressure relief devices. So if there is a fire, it will open and vent all of the hydrogen to atmosphere, as well as other pressure relieving devices. So if there's ever a pressure for any reason it's pressurizing over above where it should be, it will release pressure and release the gas. Um, Another place that people don't really realize is that on the dispensers, if you're going to go fill up a vehicle at a dispenser, based on the international protocols for how the dispensers work, when the dispenser turns on, the first thing it does is and you hook it up to your car. The first thing it does is puts a slight pressure pulse into the vehicle. That'll open up the receptacle. It's got a check valve in it and needs a little bit of pressure to open it. It'll open up the check valves in the system, and then the first thing it does a leak check on the vehicle and a leak check on the dispenser. So you have a high pressure gas that you're going to be putting into a vehicle, and every single time you fuel, it will go ahead and do a leak check, both at the beginning. There's two different protocols: one at the beginning, one at the middle, and one at the end, or just one at the beginning and one at the end. It will go ahead and verify that there are no leaks within that system. Um, which is pretty interesting because that means that literally every single time you use it, you're going through a safety check. And obviously, there's no way with a gasoline vehicle that we're ever checking for leaks. The only way you find out is if you find the stain on your driveway. So very safe from a fueling perspective, from how the fueling systems work to be able to go ahead and fuel up. This is an example of a particular fueling station that's been designed in Vienna, Austria, and it was on tour running around Europe at one of our Swijack facilities, and that's why you see it here. There's a sub myth, and we hear this every now and then, which is just really quite not true, about automotive manufacturers aren't convinced about its safety, and that's not really true at all. There's multiple international certification programs that really ensure the safety of hydrogen as a mobility fuel. For instance, Toyota has received approval from MITI, which is the Ministry of Economic Trade and Industry in Japan, to self-inspect and manufacture their hydrogen tanks for their fuel cell vehicles. If there's anything in the automotive industry, one of the concerns is just the availability of fueling in different areas. And we'll talk a little bit about that later and how we're doing that to be able to build the environment larger for hydrogen. They're just not going to, many companies aren't getting into hydrogen yet until there's more fueling stations. So one last thing is that to ensure safety and the growth of the industry, there's many of us that work within the codes and standards for construction of fueling stations and for vehicles throughout the world. These are some of the different groups that are involved. ISO for the entire world. The CSA group is the North American Gaseous Fuel standards committee. So CSA takes gaseous fuels in North America, Underwriter Laboratory in the US does electrical things, and then we share across borders. So we have representatives from both countries. We have the European Commission, the EN or EU, which writes standards for in Europe. The one in the middle is the United Nations, and there is a United Nations group that writes the global technical requirements for hydrogen, and then a variety of other ones in other countries like JIS for Japan, Korean KSA and KGA for Korea, and a variety of other ones as we go around the world. Each one of these standards groups we try to harmonize as much as possible. So if it's for safety, we try to write the standards so that those same safety protocols work in different standards around the world, and we share a lot of the same requirements. There's slight differences in some countries for a variety of reasons, but that allows us to manufacture products that then have a global reach. So just to recap, hydrogen being safe, safe to use. Hydrogen presents the same, if not less, dangers than other fuels, because it's non-toxic and it's got low hazard characteristics within the use of hydrogen gas. I'll mention the other thing just real quick. There is the other use. Hydrogen can come in liquid form as well. It's very, very cold. It's minus 353 degrees Celsius or 20 degrees Kelvin, which is one of the coldest possible things we can make. Of course, when you get that cold, you always have cold dangers of cold burns and other things and lung issues. So there's always care being used whenever you're dealing with liquid hydrogen, but no different than if you were working with liquid oxygen or liquid nitrogen. So that pretty much fits in the same dangers hazard areas there. There's there is an array of different safety protocols and procedures that are implemented throughout the world and used at every design stage for every piece of equipment that's being built, whether that be a dispenser, whether it be a transport truck, whether it be heavy duty trucks moving goods across countries, or whether that be small vehicles. Or more importantly, there's also an important fact that the most hydrogen vehicles in the world right now are actually tow motors or lift trucks being used in large warehousing areas like Walmart and Amazon. They work really, really well in that environment. And then hydrogen obviously promises efficient and economical solutions when handled safely and going into the future. So how does Swagedock fit in with this? We are kind of being a little Swagedock centric in a few places here, but we have a 75-year history of being one of the top premium quality leak-free solution providers for all kinds of different industries, but of course H2 and on-vehicle applications as well. We've designed and engineered, manufactured with safety concern for these small molecule gases. Having been, from a personal standpoint, having been in the design loops of many products, the most difficult thing to design for is small molecule gas. Gas leak seal performance is very, very difficult to deal with. These molecules are extremely small, and it's very hard to seal against them. So it takes really a lot of diligence in the design process in order to be able to hold back, keep hydrogen, especially from leaking. So an example of one of our products, and this is a key fitting technology that we have for the hydrogen industry. This is the FK fitting. It was designed back in about 2004 or 5, way back, if anyone remembers, when George Bush was president of the United States and said we were going to have a hydrogen economy. Well, it's here. It just took another 15 or 20 years to get here. But we designed this specifically for on-vehicle hydrogen performance. It is a 2-ferrule fitting. It follows the 65 years of Swagedock experience. And personally, I was on this design team, and this is actually one of the best fittings ever made in the world, as far as I'm concerned. It's designed to do a lot of things within hydrogen specifically. And I'll give you an example of what some of these are. Just a quick cross section. We're not going to get into a lot of detail, but 2-ferrule fitting. There's a back ferrule and a front ferrule. This is a female body, so a male nut that comes in behind it. But the difference between this and other 2-ferrule fittings that you'll see in the market, the first thing is the front ferrule is the most important component when you deal with gas seal performance. That front ferrule and the body have slightly different angles. So as the rear ferrule pushes forward, as you go ahead and advance the nut, what will happen is there's a variety of angles and radii that help force that front ferrule to do 2 things. It dives into the tubing. So it actually gets under the surface of the tubing. So minor scratches and imperfections on the tube do not affect gas seal performance. That's always been a challenge in ferrules throughout the world. So we designed this one to do this. As well as we have a long, very long, fine finished area along the body and the front ferrule that gives us a long area to resist any kind of molecules coming through. The back ferrule hinges and collets to hold onto that tubing, and this will actually hold 4 times the burst pressure of the tubing. This has actually been rated to 20,000 psi, so we can do 4 times 20,000 psi, so 80,000 psi for burst. So sometimes arguments of saying other technologies can't possibly blow out or burst. Well, at 80,000 psi, I don't see us getting that pressure very often. This is pretty much blowout proof as well for that reason, because the way this is designed, as long as it's installed properly. When we talk about installing properly, we have a gauge that will actually allow you to check and make sure it's been pulled up enough, as well as it's a makeup by torque and a makeup by turns fitting. So it meets up needs from large manufacturing and other areas. Last, there is an innovation that Swae has, which is what we call our SAT12 process. It's a low temperature case carburization that we can do on stainless steel. We can get the stainless to be as hard as tool steel without losing ductility. We do that process on both the front and the back ferrule in the FK fitting line to allow us to get an additional dive or bite onto that into the tubing in the front, and that allows us to also get additional tube grip at the front of the ferrule. So as you're looking at using different products within hydrogen, the leak-free performance on this is fantastic. We have it on vehicles right now. They're all being tested for heavy duty, major platforms around the world, as well as looking at infrastructure. So it is a much better application for hydrogen than some of the other options that are on the market today. All right, so let's go look at the next myth. So our next myth is hydrogen is not a practical long-range solution. So something that's going to be out there for a long time around the world. Well, there's a few things about it. Hydrogen has a very high energy density. In fact, it's the highest energy density of any of the fuels that we have out there within the world. Now, one of the things about it is it can deliver, when we use it in, let's say, a vehicle, we can deliver comparable range, if not greater range. And when it's pressurized and stored on a vehicle, it can be distributed effectively and pretty much as easily as carbon-based fuels. So we can fuel a vehicle that would give approximately a 350-mile range with hydrogen under current conditions today, and it's being done around the world in 3 to 5 minutes, about the same as it takes to fill up with gasoline. And there are new protocols coming for heavy duty that'll fill trucks very, very quickly as well. One thing about hydrogen, it truly is the most abundant element anywhere in the universe. But here on Earth, H2 does not exist in its own form. Hydrogen is always kind of tied up with something else. So, of course, our classic example is water, H2O. And other organic compounds. So there's lots of different places. Hydrogen is part of methane. Methane is CH4. So if you can break the hydrogen off of whatever it's connected to, you can end up with pure hydrogen. One way to do that is electrolysis, and we have a picture down here of what electrolysis does, and it's a very, very simple formula. It's water plus electricity equals hydrogen and oxygen. And then on the flip side, when you go to use it, if you take hydrogen plus oxygen, you end up with electricity plus water. And that's basically how the whole thing works. There's an anode and a cathode, a power supply that comes into the water, and basically you create off the cathode side hydrogen bubbles and capture that hydrogen. Off the other side, it's oxygen that can do one of two things. It can be vented to atmosphere or used for other industrial uses. There's no loss of either hydrogen or oxygen in this process. Now, one interesting thing is that other fuels, like gasoline and diesel fuel, all have to be refined from oil as well. Whether that be any other source of liquid fuel is still refined as well. So we end up having that while there is a treatment that has to be done to make the fuel usable or make hydrogen usable, there's also a treatment needed for every other form of energy that we have. So There are major sources of hydrogen today. The primary way that we make hydrogen today is a process called gas methane reforming. So we take natural gas, we knock the carbon off of it, and you end up with hydrogen. It's a multi-billion-dollar industry around the world. Generally, these places, if you see a gas methane reforming plant, it's going to be look like a small power plant. They're large, they're industrial, but those are starting to come down in scale, and they're getting smaller. There's companies that are making smaller scale reformers that can go right at a gas station, about the size of a container, a shipping container. Sit in the back of the gas station and make hydrogen all day long from natural gas. The reason that's an attractive option at this moment in time is that, like in the United States, we've got trillions of miles of natural gas lines running around that we can grab natural gas easily. So that's one way to make hydrogen. Um, Another thing we can do with hydrogen, a little picture at the bottom, and this is actually showing we can move hydrogen through our natural gas network by adding more hydrogen into the methane stream and then pulling it off on the other end. And there's some projects working around the world on that. We'll look at a little bit more of that later. And then, of course, there's other sources of renewable energy. So right now, solar, wind, biogas, and other fuels can be used to generate electricity for electrolysis. Electrolysis is truly the clean way, and ultimately, we'll talk about that as green hydrogen. We'll look at that a little bit later too. But we're going to go ahead and separate oxygen and hydrogen. One important fact about wind and solar is, of course, the wind doesn't always blow, the sun isn't always shining. But when they are, um, if you're not using all the power that they're generating, so for example, there's places on the North Sea that the wind blows really strong at night and not so much during the day. So they need their big power and their big industrial uses, say in northern Germany, are using a lot of power during the day, but not so much at night. So what do you do if you've got a lot of wind? Well, instead of using that wind to take power to the grid, you can take it and make hydrogen all night, and then the next day convert that hydrogen right back to electricity and sell it back to the grid. And the way spot pricing works with electricity, they've found a very good economic trend to be able to do that within some of those regions. So we typically call that power to gas or power to power. So it is actually power to gas back to power. Um, there's one interesting thing about infrastructure, and we'll be seeing this starting to happen in more and more places. While there are standalone hydrogen stations, which are usually there for demonstrators and early purposes, what we're doing now in many areas. So right now there's I believe it's 47 stations in California that all are built. Well, almost all of them are built at other gas stations. So they just take over an area in the back, put in what's needed for the infrastructure portion of it, the gas storage and compression, and then additional pumps that work the hydrogen. Same thing in Europe. There's about 160 stations in Germany right now. All of those are built at standard gas fueling stations. So you'll start seeing that popping up in a few years around the country. More often in the United States, what you'll be seeing is you'll be seeing heavy duty. So those are going to be going into places like TA, Travel America, truck stops, as well as other major on highway areas for both, for all mostly heavy duty in the US. There's light duty as well in Europe. And then there's the important thing about hydrogen is that we oftentimes think about this as a transportation fuel, but there's a whole lot of other things that it can do. Um, we see it in transportation. This is part of the universe again, just in a different way of looking at it. A large application we're seeing right now is stationary power. So when we talk about stationary power, think about your Microsofts of the world and your Amazons. They have data centers, usually very nondescript buildings stuck back someplace that you don't know even what they are. But that's where their data centers are for their computers. And right now, what they have sitting behind them is a big, ugly diesel generator that is their backup power. So if the power goes out, that's how they're going to get power to keep the data centers running. Um, in the Microsoft area, I think they've got something in the neighborhood of 50 or 60,000 of them, and they're building 15,000 more a year. They want to convert all those over to hydrogen. So there are people that are building on-ground storage. Basically the exact same system that we put onto vehicles, except there's no vehicle. It just goes right into the building as power. Other we mentioned chem and refining and other industries like glass and steel earlier. There is the ability to use hydrogen directly into power generation. Siemens does make injectors to go directly into gas turbine engines and bring in either pure hydrogen or hydrogen mixes into gas turbines that are used for power generation today. So, and eventually by 2050, Los Angeles is planning on all of their generating capacity being done by hydrogen. And they're using that through what will start off as being gas turbine generating facilities. Public transport is a large area that we're using that is already going to hydrogen. Many of the buses at LAX are hydrogen today. There'll be a large push to move to hydrogen buses for public transportation inside of large cities. There's a large push for this in Europe. There's many buses being built in Europe. And then transportation and road freight. We really see road freight as being one of the large places to see hydrogen being used. The reason is, and there's always a discussion about, is battery electric or hydrogen going to be the next phase? A lot of people feel that that electric cars are the way to go, and they are if you don't have range anxiety. I drive way too much to have an electric car. I would be spending my entire life charging. And for large trucks, the amount of batteries it takes to take a large truck a long distance, like between interstate areas or intercountry areas in Europe, is really restrictive to losing weight that you can actually transport in the vehicle. So hydrogen is a much better option for that. And then you'll see things like we can actually make hydrogen right off of hydro dams and wind power and solar power and backup systems and so forth. There are projects going on around the world to bring trains up, both commuter trains in Europe and large freight trains in the United States and Canada, looking at using clean hydrogen. And if you think about trains, and many of the large ships that use azipods, those are all electric motors that run those vehicles. So you're just changing out what your power source is to switch over to hydrogen. And the last one for shipping is there are new rules going into effect around the world that are not allowing large, even cruise ships, to be able to run their heavy oil power plants when in port. So they have to find another way to do that. And hydrogen offers a really great opportunity to be able to switch over from running large diesel or fuel oil engines while in port to generate electricity for that particular ship while you're there. So finally, just to recap, some of the long-range solutions, because of hydrogen's high energy density, it's particularly well suited for like heavy-duty vehicle applications that we just said. It's lightweight and can be used to maximize the truck's payloads over batteries, dramatically increase their range. High-speed refueling, I mentioned this a little bit earlier. There is an industry consortium working on very high flow, high speed refueling for trucks. So that a truck could put on enough hydrogen to go between 700 and 1,000 miles in less than 10 minutes. So that really allows you to reduce downtime for fleets. And if you think about it, that would mean to get across the entire United States would take no more than three fills, so 30 minutes of fueling time, which is very low. If you were trying to do that with battery power on a truck, it could be 9 hours per charge. So that doesn't work really well. And then finally, that whole part about the lift trucks. Lift trucks are filling in 2 to 3 minutes, and then running a shift or two within a warehouse. And you don't get the fumes that you get from propane, and you don't have the problems with big heavy batteries and leaks and all the other problems that happen there. So even though green hydrogen depends on wind and solar power for generation, as we improve storage technologies and create new ways to store hydrogen, it helps keep the energy flowing regardless of what the weather is. So having fuel cells on site you can store the extra energy when the sun shines and use it again when it gets cloudy outside. So how does Swagelok fit within this long-term durability and long-term infrastructure? One thing that we do is we meet the challenges for these applications that are planning on being out there for 50 years. Hydrogen has an effect on materials. Hydrogen is so small, it can get up inside of metals and cause them to do something called embrittlement. So hydrogen embrittlement is a concern to have. The way we hedge against this is we've worked extensively with various labs around the world to look at what those levels within the stainless steel that we use need to be. And nickel is one of the elements. Nickel is the single most expensive element inside stainless. And the typical requirements for nickel are between 10 and 14% nickel. Swagelok uses a 12% nickel. There is a curve that hydrogen embrittlement takes off. It gets a lot steeper. below 12. So we are 12 or above in all cases. And then the other picture on the other side, we're looking at some corrosion issues happening here. Corrosion, one way to really protect against corrosion is to increase your chromium value within the steel. So we bring that up to 17% to help with the corrosion, and that's everything from crevice corrosion to pitting corrosion that can take place. If you start corroding, the hydrogen can get in there and help nibble away at that as well as part of the embrittlement process and have a lot of other problems. So having a good product in the field that is has great longevity requires both resistance um, against embrittlement as well as resistance against corrosion. So here's a big one today. Hydrogen is too expensive. Another myth. Um, the price of green hydrogen continues to fall. The prices of hydrogen around the world are falling. We've been making industrial hydrogen, in many different forms around the world for years, but now we've got a new type of industry to deal with, and where we make the fuel is not always where it's needed. So as more and more production comes online, what we'll see is continued dropping of those prices as we go through time. It is projected it'll be considerably cheaper than natural gas by 2050, or if the economic trends keep going, probably by December. I don't know, just because our gasoline and all the other fuels are getting really expensive. But the processes for developing hydrogen are well, it takes equipment and it takes different things in different places. The more we have, just like all economics, the cheaper it'll start getting. And so there's ways that we're dealing with this. So one thing that the government is doing is helping push some programs together, because it's really hard for private industry to go ahead and do all the investment necessary. Right now, what the U.S. has done, and this is the Department of Energy, and they call these things Earth shots. This comes from the concept of JFK's "we're going to go to the moon in a decade," and that whole challenge they gave in the '60s. And there's a few different Earth shots for hydrogen. This one particular is the $1 US dollar for 1 kilogram of hydrogen in 1 decade. So in 10 years, getting the price of hydrogen down to $1. That will be a game changer with hydrogen in the industry. Right now at the pump, it's anywhere between $7 and $15 in Los Angeles, where it is commercially available. So that price needs to come down, and it will. And it has been, and it was starting to more and more as we get more and more usage out in the market. In Europe, there's another similar project going on. This is called the Backbone Project, and this is actually pipelining processes to move hydrogen around. You just kind of see the spider web here of all of these projects that are going. And there's lots of different things they're doing, including storage underground in salt caverns. So we're doing large scale hydrogen storage underground, which is one of those improvements in storage we talked about a little bit earlier. But this whole project is part of a many billions and actually trillions of dollars of investment that's going on in Europe now for hydrogen and hydrogen infrastructure. You can't use hydrogen if it's not there. So you've got to get it there. That's the first thing. And then the second thing is then being able to build the infrastructure to be able to fuel vehicles or use it in homes or however you're going to use it within those areas as well. But then obviously it's easier for the vehicles to come. As we mentioned earlier, the cost and efficiency of renewable solar, wind, water energy sources are continuing to improve, and this will carry H2 fuel costs with it. We're gonna have some problems with solar for a while. A lot of the solar panels are stuck in China right now due to COVID, so it's going to take about a year for that industry to recover dramatically. But there are plans in place to put in large solar arrays to do electrolysis and green hydrogen around the country and around the world. And what you'll see is that there was a report done in London looking at vehicles and looking at the combination of just so you understand the words: fuel cell electric vehicles, FCEV; BEV, BEV is battery electric vehicles; and ICEV is internal combustion engine vehicles. So those are the three different terms that are here. And what you really see is you see fuel cell electric vehicles coming down in cost per 100 kilometers, dramatically as it keeps going into the future. Battery electrics will drop as well, some, but that's completely variable on electric costs and battery production. But they're really looking at that break point, that hinge point of the cost of ownership changing around 24 between mid 2024 for buses and so forth within that industry and that study that was done in London. So one last one. I like this one. This is the surprise, the little joker that pops up. High quality components reduce surprise costs of unexpected maintenance. In a lot of conversations with station owners around the world, there's some technologies out there, fitting technologies in particular, that are used that have a tendency every now and then to leak and then heal themselves. But if you get a leak, the stations have a lot of safety on board. They have sensors, and they're smelling for hydrogen, and they're monitoring for flames, they're monitoring for heat, and they're monitoring for a lot of different things. If you set off one of the sensors, the station will shut down for safety reasons. Then you have to send a maintenance tech out there to search for where the leak is. And what they found in certain cases, they can't find it because it fixes itself. But taking a station offline, it is interesting. You talk to hydrogen users in California in particular, and as soon as a station goes offline, Facebook blows up and says that station's closed. So it's bad for reputation, and it's bad for the industry to go into unexpected maintenance. So high quality components can help reduce those surprises and keep those stations up, keep them running, keep the infrastructure up and running for long periods of time, and not disrupt the supply of hydrogen to the customers. So we mentioned before, the government support will help accelerate the growth of hydrogen at scale. In the U.S., one of the big plans is to go to hub and spoke. So we're going to build centers of large hydrogen production that will then supply areas around them within the country for that hydrogen, and the government's helping support a lot of those programs now. The price of green hydrogen continues to fall along with the compared to the other mobility fuels, and it's projected again to be cheaper than natural gas by 2050. These numbers and some of these statements may only be 3 months old, but they're still dated due to what's happening in the world economy today. So we will see how that goes, and I think hydrogen gets more and more attractive as we go. As the cost and efficiency of solar, wind, and water power really helps reduce the H2 costs as we move forward. So how does SwageLock help with this total cost of ownership? Well, the key to lowering cost is scalability and increased infrastructure. So we can help with this with product and solutions and services. So SwageLock total cost of ownership, and this is one of the value statements that we talk about all the time for refueling infrastructure, includes your reduced installation time, ease of maintenance, long service life with corrosion resistance and embrittlement protection, and then standard solutions for global support. We have solutions engineers that can help design systems that are both efficient, easy to maintain, and can be delivered as a package. So a portion of a system can be delivered with one part number coming directly from SwageLock assembled, making it easier to install and have standardization in facilities around the world. So I think that's our last myth, which is hydrogen is not environmentally friendly or sustainable. So really, hydrogen fuel cells create no smoke, no waste, and the only output are energy and pure water. And when I say that, it is distilled water, so you can actually drink it right out of the tailpipe of or a drain pipe out of a hydrogen bus. So hydrogen is very environmentally friendly when it comes to what kinds of things and wastes are we putting out into the world. There is, however, the production side, and that is one of the discussions, and this is where the industry is moving today. There's we can create CO2 during the production of hydrogen. These are 3 of the colors. There are rainbows of colors. All the rainbows are not the same. Everyone doesn't always mean the same thing. Generally, these 3, gray, blue, and green hydrogen, are the same in most of the different charts of colors that you see. Gray hydrogen today uses CO2, uses a fossil fuel, and what you do is you get CO2 and hydrogen out of it when you break down through steam methane reforming. Oftentimes in the past, and still today in some areas, CO2 is released into the atmosphere, so we do get a CO2 hit from that gray hydrogen. There's also one called black hydrogen where we can make hydrogen from coal. So the next trick is, though, and where everything's working at now, there's lots of work on this right now, is carbon capture and storage. So capturing that CO2, capturing that carbon, and then sequestering it in some way that is safe. Some of the neat ways that are doing it, so there's some groups in the Netherlands right now that are capturing the carbon, turning it into carbon uh, powder, and then mixing it with cement and using it in the roads. So it's pretty much encapsulated and out of the environment. Other places are they're pumping them down into old aquifers or old wells underground for deep down storage. Um, and there's a variety of other things. The cool one is the people that are trying to take the carbon we get from making the hydrogen through methane reforming, and then capturing it and creating carbon nanotubes, which is what we'd use to make carbon fiber, to make more tanks for more hydrogen. That's the cool one. I like that one the most. And then there's green hydrogen, where we come in and we bring in water and renewable energy, and what we get is net zero emissions of CO2. So that's the ultimate goal. And these are happening, and they're getting larger and going more at scale. And we end up with hydrogen and oxygen as our two outputs. So that's where everything is moving to. The other two, gray and blue, are out there in the world, and that's predominantly where we're getting our fuels from right now. But the goal is to really move towards green, both in North America and in Europe, as well as Asia. I mentioned earlier about carbon capture and permanent storage for and industrial uses. There are key areas around the United States where hydrogen hubs would make a lot of sense. You kind of see, with the exception of the South, I don't know why the Eastern Seaboard in the South, there's really nothing there. But within a lot of these areas are a few different things happening: heavy industry, or natural gas formations underground, where carbon capture could be done underground. They also sit along major freight routes within the U.S. So these are being targeted areas to do both hydrogen development for fuel and carbon capture for both industry and for hydrogen, to be able to capture that carbon and start reducing that amount of carbon that's going up into the atmosphere. Another thing is we talked about those Earth shots earlier. There's a few of other ones going out right now, and the first one came out in June of last year, and that was the one for clean energy, reducing the cost by 80%, getting that $1 per kilogram. There's another one, which is long duration storage, which aims to have affordable grid storage for clean power, which basically means we start storing up to 10 hours of power on our grid. Right now, in the United States, we do not. There's very, very low storage for electric. We store about 60 to 80% of our fossil fuels someplace, whether that be in salt domes, whether that be in refineries, whether it be in pipelines or in your car, at gas stations. There's a lot of storage of fuel. Electricity, we store very little. It's like, I think there's five zeros, so it's 0.00063, I believe was the last number I heard, of electric power stored, and that number keeps going up because we keep having more cell phones and we store power on the batteries. But large scale storage of electricity doesn't really exist. One of the goals is to get there. One way to do that is with hydrogen. There's been talk about using megawatt scale batteries for cities for backup. The only problem is a megawatt of batteries would take about a city block square building 4 stories tall, to be able to go and store that much energy. So that doesn't seem really viable, and lots and lots and lots of batteries going inside of it. So long-term storage is another goal that's coming out. And then finally, there's this carbon negative, which is working towards reducing hydrogen or carbon within all approaches, from both the atmosphere and meaningful scales over the next few years. And hydrogen is a great way to be able to do that. So, facts, recapping that, hydrogen fuel cells create no smoke, no waste, and just water and electricity on the way out. There are several processes in which hydrogen can be produced. The processes have wildly different amounts of CO2 emissions and sustainability, but we're working towards the greener initiatives as we move. And the government efforts, such as the Earthshot programs, are helping support long-term growth. So we talk about SwageLock and clean energy, and we've been this is our 75th anniversary, so we're celebrating that this month and next month. And we've had 75 years of experience and expertise in containment and management of small molecule gases under pressures and under medium to high pressures, which is where this entire industry lives. For the last 30 years, we've been working directly within the clean energy groups, working with natural gas, Natural gas on vehicles has evolved into hydrogen on vehicles. So many of the same players are playing in that market. The things we learned from natural gas are helping accelerate the hydrogen development, stations on vehicle development, and so forth. But small molecule gas is, hydrogen is dramatically smaller than natural gas as a molecule size. Our stainless steel components deliver leak tight systems and long service life due to our designs and due to our materials. And then we, of course, have a global network of authorized sales and service centers, experts around the world in Swagelok product, in the industries, and they're there whenever and wherever and whenever needed to help support the industry. And as a result, we are uniquely qualified to help customers meet and overcome fluid system challenges unique to this clean energy industry. So, John, I will turn it back to you.
Well, thank you, Chuck. We have got about 10 minutes left, so we will take as many questions as we can during that period. But we will follow up with anyone who submitted questions that we don't have a chance to get to. The first one comes offline. Um, how will the sunsetting of the EC79 certification impact the hydrogen fuel industry?
Okay, this is interesting. For those that do not know what EC79 is, EC79 was a component-based certification in Europe required for all components that went on vehicle. As of, I believe it was July 6th of this year, it has gone and been sunsetted, which means you can no longer certify product. The industry is still trying to figure out what exactly is going to happen. They've replaced that requirement with a full vehicle certification test called R134. It doesn't actually test individual components. It tests the whole vehicle as a whole, including things like, will it vent properly if it's upside down? Will do the lights work on the danger lights work on the dash, and how does the high voltage system work? I think over time, one of two things is going to happen. We're either going to put back in individual component requirements, or people will continue to get testing done to the protocols of EC79 and then have test reports that meet that need. So when a vehicle manufacturer goes through a process called homologation, when they get the whole vehicle certified, they will have the backups that they need for it. We have extensive parts that are already certified EC79, and then there are other international standards. There's certifying standards include the HGV standard. HGV 3.1 for individual components may also be used. That's a North American.
Okay, and just as a reminder, if you do have a question for Chuck, you can add it to the Q&A in the chat box. Second question, I have heard that 13% nickel content is actually the best for hydrogen applications. Why is Swagelok at 12%?
It's a very good question. So 13% is very true, but it's only looking at one element within the steels. There is a requirement actually in Japan that all the materials are 13% nickel, and another number which is called nickel equivalency of 28.5. What we feel is, from our standpoint, we've done extensive testing in partnerships with Sandia National Labs and other national labs and organizations around the world, is that we found that a 12% minimum protects significantly against embrittlement, but also allows us to manage other elements within the stainless. So we have a dual graded 316L material with sulfur contents that are controlled for weldability, with carbon and moly to help stabilize the crystalline structure of that material for longer life. And at the same time, resist corrosion. So in order to, most of our materials meet the 28%, 28.5% nickel equivalency. Our minimum is usually 27.5. They come together, and there's different arguments about this. Some of these numbers came from universities that offered these as suggestions, and they got introduced into standards. We do know that 10% nickel really offers considerable reduction for reduction of protection from hydrogen embrittlement, or reduction in the time that hydrogen embrittlement will take place. And one of the very things to be careful with is most stainless steels that are not specified are made at 10% nickel or 10.1%, just due to the costs. We feel 12 is the right way to be, along with that chrome and the moly stabilizations.
Okay, thank you. Here is a question regarding the FK fitting. How does the design work with two ferrules biting into the tube? Can the tube be reused and serviced after the initial installation, or can it only be used once?
That's a kind of a double question. The answer is that we do plastically deform the ferrules to be able to get the grip onto the tubing. Um, Therefore, that grip can only be made one time. However, the fitting is remakeable up to 25 times. So that same joint can be remade up to 25 times, and that's certified. It can possibly go further, but that's what we guarantee. Um, so you can actually take that fully apart, put it back together, re-pull it up, um, add an additional, slight additional torque to it, or slight additional advancement of the ferrules of the nut, and it will reseal every time. Um, the reason you can't take them off the tube is because they have gone ahead and formed into the tubing to be able to get that pressure hold. So you can remake the fitting, um, and that fitting would be the tube and the ferrules already swaged. Once that swaging action takes place, you can't actually remove the tubing and reuse the tubing.
Okay, we have a question from Janet Goss. When you mentioned the long service life, and the corrosion resistance, what is the expected long service life? Are we talking 5, 10, 15, 20 years?
So generally, when you go through corrosion testing, it'll go through a series of international standards. I can't rattle those ones off the top of my head. But we do salt spray corrosion testing as a highly accelerated test in the labs. The hydrogen standards require a 144-hour test, which is equivalent to 20 years of service life. We have additional testing that we have done, including up to 500 or more hours of corrosion testing and salt spray corrosion testing on different products over the years for different reasons. But generally, you're looking at on vehicle of being a 20-year life. You're looking at on station of being between 20 and 50 for any of those environments. Now, one of the things to know that is that Swagelok uses the same stainless in a lot of our different industries, including offshore. So we do have a lot of experience being in highly corrosive environments and holding up for a long time.
Okay. Next, why don't I see hydrogen powered vehicles in my neighborhood?
Great question. Um, we are just coming out of, if you think about the development curve for any new industry, you're going to have the point of prototyping and proof of concept and early engagement occurring, um, and then moving into early adopters. So in North America, if you were in Los Angeles County, you might see a hydrogen vehicle coming down the road. So there are, Hyundai has one of their large SUVs, Toyota's there obviously with the Mirai, the Honda Clarity is in place, and they use the fueling stations that are in that area. It's 8 to 10,000 vehicles within Los Angeles County, I believe, is the number. But right now, if you're in Cleveland, Ohio, you're not going to see a hydrogen vehicle anywhere unless it's potentially a prototype bus that has its own station. So right now, it's the combination of chicken and egg discussion. So which comes first? Do you build fueling stations first, or do you build vehicles first? There is one company in particular, a large trucking company called Nikola, which is developing both at the same time. So they're coming out with a concept to build stations throughout the country and corridors for hydrogen, as well as heavy duty trucks that can use those corridors um, and fuel at their stations that they're helping to work to build, so that the chicken and egg is solved. How long will it take? It's going to take another 5 to 7 years before we see the real heavy duty industry moving in large volumes. So large volumes are really starting to project out in 2030. Um, in Europe, it's a little bit faster. They've been building stations for a little bit longer, but a lot of theirs are using a little bit lower pressure containment amount. They're using about 350 bar or 6,000 psi versus some of the new ones that are coming out at 7,000 or 10,000 psi, 700 bar. So as we develop stations and build them out, there'll be more and more vehicles and more access.
Okay, we've got time for one more very quickly. What are the factors that make hydrogen fuel so expensive to produce right now?
It's actually the production doesn't cost it. The production itself is not terribly expensive. So if you're doing a gas methane reforming, we can be doing a kilogram of hydrogen around $1 for actual production cost. It's the next phases of it that cost money. It's moving it around on trucks. It's the filling up of a truck. A large one of those large tankers, like we showed earlier, can take 10 hours to fill. And then you've got to get out on the road with that and move it around. So it's the movement of it. It's moving it into stations. It's compressing it to pressure. Those are the things that are costing right now. As we move to more localized production, so even at station production, we'll be able to use hydrogen to create energy to then use the compression, and that'll start bringing down costs as well. So there's right now it's just the scale is not there, and the location of where the hydrogen is versus where it's needed is not there. But there are changes happening. Just 2 weeks ago, we opened a brand new the liquid hydrogen station in Las Vegas. So that was a great add to our network,
Yeah,
the
excellent.
global network. Yeah.
Thanks, Chuck.
Yep.
Well, we need to wrap up very quickly. If you would go to the next slide, please.
Sure.
You can request more information from Swagelok by following the link presented right there. That will take you to a page where you can be matched with the sales and service center in your area. Typically, we'll get back to people who make that request within 3 business days. We will be making an on-demand version of this webinar available on swagelok.com, and that should be posted via that link by the end of this week. And as always, you can stay up to date with Swagelok by following us on our social media channels. So at this point, I will thank you all for your time and attention. We hope you found it helpful and informative, and we look forward to hopefully seeing you in the future. Thanks very much.